Can you see my screen?
Uh-huh.
Yeah,
So which problem are we looking at?
I did read.
Number one
I did.
or
I already did this, but I did two mistakes here, and the other one. Wait, scrolling down. Mm, yeah, this one.
number eight?
Yes, number 8.
So it asks you to explain what's going to happen if we apply De Morgan's law to that expression. And then what happens if we apply the double negative laws and the distributive laws. You have to look at theorem 2.1.1 in the book. So hang on, I'm gonna get I'm gonna get theorem 2.1.1 up so that we can look at it together. Okay. And then that will help because it's helpful to look at those laws so that you know what it is that is going to happen under the influence of those different laws. Okay. So if you stop sharing, then I can share. All right. Let's see. It's the summary of logical equivalences. I'm going to share my screen here. All right. Can you see it?
Yes, I can see. Okay. Um,
Trying to make this a little bit bigger. So we have the commutative laws that tell us, that the and operator doesn't care which side the Q is on or which side the P is on. Okay. And
mhm.
same with the or operator. Those are the commutative laws. It says P or Q is the same as Q or P. Okay. Now the associative laws say if all we have is and operators, it doesn't matter whether we evaluate P and Q first or if we evaluate Q and R first. You see, it says it doesn't matter which you do first if it's all ands. Same way with if it's all ors, it doesn't matter if we evaluate P or Q first or if we evaluate Q or R first. It just doesn't matter. You're going to get the same thing.
Mm.
The distributive laws show us how we can distribute the and operator across the or operator. It's kind of like the way the times will distribute across addition. Okay, the and will distribute across the or. So P anded with the quantity Q or R is the same thing as P and Q quantity or the quantity P and R. So the and can distribute across the or. And in a symmetric way, the or operator here, P or, can distribute across the and operator. So P ORed with the quantity Q and R is the same thing as P or Q and P or R. And then we have the identity laws that say if you take P and you and it with a tautology, that's the same thing as P. Or if you take P and you or it with a contradiction, that's still the same thing as P. And you can check that with truth tables,
Mm.
And the negation laws say if we have P or not P, well, that's always true. So that's a tautology. And if we have P and not P, that's never true. So that's a contradiction.
Mm.
That's the negation laws. The double negative says not P is P, right? The idempotent laws say if you and P with P, it's the same thing as if you just had P. Same with or. P ORed with P is just P. And then there's the universal bound laws that say what happens if it's P or a tautology. Well, that's always a tautology. Or P anded with a contradiction. That's always a contradiction. Here's De Morgan's laws that tell us how the not distributes, right? You know that law across the and it tells us also how the not distributes across the or. Here are absorption laws. P ORed with P and Q is just the same thing as P, and P anded with P or Q is still the same thing as P. And then the negation of the tautology is the contradiction, and the negation of the contradiction is the tautology. So these different laws tell us logical equivalences. Okay, these are laws about logical equivalences. Now, hang on. If we look at this problem that you were looking at, problem number 8, okay? And it's talking about how this expression, not P, anded with not the quantity not P and Q, is going to give you a circuit. There it is in A. And not P or Q gives you this circuit, B. And it says fill in the blanks to prove that the circuits will have the same input-output table. Like you can find their IO tables and they will be the same. But it's what they're really asking you to do is look at that table and decide how we could use De Morgan's law to change this expression right here into a logically equivalent expression, and then use the double negative law and the distributive law and the commutative law. So it's actually, you know, necessary. I'm looking for the book. I'm looking for the content. There we go. You know, you kind of have to use 2 screens so that you can see the laws of logical equivalences. But we can go back and forth from WebAssign to this table of logical equivalences, and let's see if we can figure it out, okay? All right, so the first law we're going to use is De Morgan's law. So, because that's what it says. It says by De Morgan's law, we can rewrite this expression as something that's logically equivalent. Okay? Do you see how De Morgan's law is going to show us how to distribute that not right there across not P
Not
and with Q?
like it will be just mm, like
Well,
P or
yeah, it will be eventually, but first it's not P.
yes.
And then the and switches to an or, right? And then the Q becomes a not Q. So if we look through this not P is still there, okay? So we'll just ignore that. But if you look here, it's not P and, because that's this and right here, is this and. And then this not gets applied to not P, that this and changes to the or, and the not gets applied to the Q. So this is using De Morgan's law right here. This
Okay.
choice. Does that make sense?
Yeah, I get that, but the not P becomes like just P, right?
Yeah, and that's the double negative law,
Mm.
right? Because the double negative law says not P is P. So that'll be our next step, right? Where this not P will just become P. So it will the logically equivalent statement still has the not P
Mm.
and P or not Q. See? Because when we get from the not P to just the P, we've used the double negative law to get from this first window to the second one. Does that make sense?
Okay.
See, that's what it's trying to do, is trying to help you try to identify what is the name of the rule. Here it's a double negative rule that allows us to say not P is just plain old P.
Okay.
Now, the next law we have to use is the distributive law. But before we even look at the choices, let's look at what's going on here. There's an and operator that's outside of parentheses that has an or on the inside. See that?
Yes.
That and can distribute across the or. And the way it works is this not P right here gets anded with P, or this not P gets anded with this, which is not Q. I'll show you the law. The distributive law, it's right there. The and is going to distribute across the or. Now, this law is given with just plain old P, Q, R, right? But we can play the game even if the components aren't, even if the components have knots in front of them. So when you look at these different choices, you want to select the one that is going to be using the distributive law where the and distributes across the or.
P and not P, or not P and not Q. I don't think.
Or not P
Uh,
and not Q. All right, that's actually that is actually correct, but you've used two laws there. You've used both the distributive law and the commutative law, because you see how when we distribute this not P
okay.
across the and, it'd be not P first and P.
Yeah, that's one, the last one, not P.
Yeah, right. But so that's by the distributive law, you see, distributing the and across the or. But the next thing we could do is, it says we're going to use a commutative law. Let's just look at what the commutative law says. Commutative law says the and doesn't care which side the P and the Q are on. Same with the or. It doesn't care which side the P and the Q are on, because those are symmetric operators. So now it says we're going to use a commutative law. Let's see. Which one of these choices is commuting something?
Mm, the I think the P and the not P. No, I think.
Yeah. P and not P means we've commuted those two, and we've kept the not P and not Q
Okay.
right
So,
there. Okay. So that's right. That is we switched the positions of the not P with the P across this little and operator here at first. So yeah, that's definitely using good, good. Now it says we're going to use the negation law. Let's just review the negation laws. All right, they tell us if we have P or not P, it's a tautology. And they tell us if we have P and not P, it's a contradiction. So do we have a P or not P, or do we have a P and not P, or Q or not Q, or Q and not Q?
I think we have a P or not P.
P anded with a not P. And that can never happen, can it? It's a contradiction. So what would the negation law change this into? Would it be this one, this one, this one, this one, this one, this one, or this one? Let's look at the negation law again. P anded with not P is a contradiction. So we have P and not P. That's going to become a contradiction.
Oh yes, see.
See it? Now the commutative law for the or. So the commutative law for the or, says or doesn't care which side the pieces are on, the components are on. So that's the commutative law for the or. It looks like that, right? So if we apply the commutative law, there is only one or here, okay? The or is between the contradiction or with not P and not Q. So what would be using the commutative law for or? Which one would be the result if we commute across the or?
I think it's,
See the or operator in there?
I see
So there's the or right there between. So
mhm,
which ones would we choose?
but we, it's like,
Look at the commutative law again. It says if you have two components on either side of an or operator, you can switch the sides that they're on of the or operator, right? Whatever those components are, they could be compound components. You see, in this expression right here, one of the components that is being ORed together is just the simple contradiction. But the other component that is on the other side of this OR operator is not P and not Q.
can I see the answer selection? So there should be, there is not P and not Q, but I
Or
don't know.
C. Yeah.
Mhm.
Wait a minute, wait a minute, wait a minute, wait a minute. We got to go back. I'm in the wrong window. Commutative law for and was, no, wait a minute, that was this. Commutative law for and was that. Negation law was contradiction. Okay. Commutative law for or. Now that's the right window. Which one is going to be the commutative law for this or between the contradiction and not P and not Q? How about that one? Doesn't that switch their places?
Yeah, this is the best.
And now we need to use the identity law for or. Let's look at the identity laws. The identity law for or is this one, that if you take a statement P and you or it with any contradiction, it's just the same thing as having just plain old P, okay? So any statement, no matter whether it's compound or not, or with a contradiction, is logically equivalent to that statement. So here we have not P and not Q or together with a contradiction. So that's going to be logically equivalent to
Mhm. Mhm. But not P and not Q.
yeah. And then finally, the last step is De Morgan's law, where we factor the negation out of the not P and the not Q, and the and flips back to an or. That's De Morgan's law right there. And so this actually shows us that these two expressions are logically equivalent, which means it has to be that these two circuits have the same IO table. So there's two ways to get at logically equivalent circuits, right? You can do it by attacking their Boolean expressions, using these laws of logical equivalence like we did here, or you can do it by building the IO tables for the two circuits and comparing them. They'll have to be identical. So, let's see if we did this right. Okay, we did it right. Did that help?
Yes, ma'am. Thank you.
And I understand it's complicated, especially when you have to go back and forth between, a couple of windows, in your screen, but it is doable.
Okay. Thank you,
Hey,
ma'am.
Nura,
Good evening, Professor. Hello.
how are you?
I'm good. I just hopped on hoping to get some information. I didn't
Okay,
really.
go ahead.
Oh no, I was watching your work with Sunita, and I didn't get a chance to read any of the chapter. But uh,
Well,
were you?
this was the homework 2.4, but it actually refers us back to a page in section 2.1, this summary of logical equivalences, this theorem 2.1.1 that tells us all these different laws of logical equivalences, like the commutative laws. So you'll want to refer to this when you work that problem. Associative laws. Like here, it's all and operators. And the associative law says, hey, you can slide the parentheses around. It doesn't matter if we first evaluate P and Q or if we first evaluate Q and R. It's not going to matter because it's all and operators anyway. See what I mean?
I see.
So, and we played this game, the identity laws. I didn't call them that, but when we made truth tables and we looked at P ANDed with a tautology, it turned out it looked just like the same as the column for P, and P ORed with a contradiction turns out to look like P. But then there's also these universal bound laws that if you take P and you OR it with a tautology, that's always going to be true, right? So it is a tautology. And if you take P and you AND it with a contradiction, well, that's the same thing as a contradiction because it'll always be false if you AND P with something that's always false, right? So it just shows these different rules, like the idempotent laws that say if you've got P ANDed with P, well, that's the same thing as having P, If you've got OR ANDed P ORed with P, it's the same thing as just having P, right? And De Morgan's laws show up in this list. We know these two De Morgan's laws, right? And these commutative laws, we've talked about how the and operator is symmetric. It doesn't care which side each component is on. P ANDed with Q is the same as Q ANDed with P. Same with the OR, right? And the distributive laws are really interesting because they show us how we distribute AND across OR, and they show us how we can distribute OR across AND. Kind of like distributing multiplication across addition. Except you can't distribute addition across multiplication. So it's a little better than that, actually. So you can use and refer to this table of logical equivalences, Theorem 2.1.1, to help you with,
Can we go over extracting an expression from a circuit?
sure. All right. So why don't we actually extract the expression from that circuit? All right, so finding the Boolean expression for a given circuit. All right, so here's example A. If we have a P and a Q, let's say we run the P through a knot, and then we take from that and run those two wires through an and then we put that through a knot, and then we put these through an There's our output. Okay, so let's try to run through this circuit and find the actual expressions, shall we? So P is on, you agreed that P is on this wire right here,
Yes.
and Q is on this wire right here, right?
Yes.
So what's going to be on this wire?
Not P.
Yeah, so we've got not P right there. So that not P gets fed down here and goes through this gate with Q. So what is here?
Q and not P.
Yeah. Or you could write not P and Q. It doesn't matter, does it?
Okay.
The and doesn't care. Now we run that through this not gate. I want to make sure you know that that's a not gate. This is a nose here. So what is here?
So we use De Morgan's law because we have to negate that entire expression.
I think we're just going to just purely write down what this is without using De Morgan's. It's a not
Oh,
in front of Q and not P.
ah.
We won't bother with De Morgan's law right now because we're trying to read what this circuit actually says. Later, we could, once we get the answer, we could use some laws to get a simplified expression, but then that simplified expression would have a different circuit. Finally, the final output is on this output wire. So what's coming out of this AND gate? Well,
Do we need that not P?
yeah, because it's part of what's getting ANDed together. So it's not P getting ANDed together with the quantity on this bottom wire, which is exactly not Q and not P.
So we start to take the component variables after they go through the gate is when we write them down.
I think I understand what you just asked. You can put parentheses around this, but if you look at the problem number 8 in WebAssign 4.3, exercise number 8 in section, did I say 4.3? I meant
Yeah.
2.4. Goodness gracious. In WebAssign, this is the expression that they give us. And then they gave us another expression. And in that exercise, we go through the different, using the laws of logical equivalences, including De Morgan's law. I mean, that's one of the ones that we use. In fact, I think De Morgan's law is the first one. Actually, they actually wrote it like this. They wrote not P and the quantity not P and Q. They wrote it like this. Generally, we write the variables in alphabetical order. Like this, you know, I wrote it Q and not P because that's what you said, and I want to reinforce that that's fine, that's correct. But generally, we write the variables, whether they're negated or not, in alphabetical order in a given expression. Just FYI. But anyway, they come up with this.
Okay.
They mean this. They are both. They're fine. You know, they're both right. Do you want to do another one?
Yes, please.
Let's do one with 3 input variables: a P, a Q, and an R. Okay. All right. I'm going to run this Q through a knot, and I'm going to bend the wire and bring it up with this P. And then I'm going to take from R and bend, take it up there. And I'm going to run these through an AND gate. Then I'm going to take this not Q. We're going to run this R through a NOT gate. And we're going to take P, bring it down here. And we're going to run that through an AND gate. And finally, we're going to take this P wire and run it through a NOT gate. We take from the knot R, and we're going to take from the knot Q and run these through an AND gate. And then we're going to take all of these outputs from these AND gates, and we're going to OR them together. The thing to
Do we,
realize, go ahead.
oh, do we start with the Q because its gate is first?
You can start by realizing that this wire and this wire and this wire are all not Q wires because they're all touching and they're coming out. So you can sure do that. This is, this wire that comes out of here is a not Q, but it comes down here, it's a not Q here, but it also goes up in there and it's a not Q up there because these are all coming out of the same not gate that Q went into. Do you see that?
So then the first one, like P and not Q.
Yeah, this is a P wire. And what is this wire coming up in here into this AND gate also?
That's R.
Yeah, so there's an R coming in there. So what's coming out of this AND gate right here?
P and not Q and R.
Yep. And that's a complete description of an input state. We're saying P is a hot wire and Q is a cold wire and R is a hot wire. It's disjunctive normal form because it's a complete description of the input wires. All right, great. Now we've got R is here, but it goes through a NOT gate now, right? So this is not R coming out here. So this wire is a not R. We've got not Q already heading into this AND gate. What's this wire? If you back that wire up, where'd it come from? Yeah, that's our P wire. So on this wire right here coming out of this AND gate, and we're going to go ahead and write, even though the wires aren't entering in alphabetical order, we're going to write the output in alphabetical order, okay? So I'm going to lift this wire just a little bit to get it out of my way. What's on this coming out from this middle AND gate?
And not Q and not R.
P and not Q and not R. That's right. And let's see what's feeding into this AND gate. Oh, we got this NOT gate. What was feeding into this NOT gate?
P,
Yeah, so this is going to be
Not
not P.
great. So what comes out of this AND gate? Look at everything that's feeding into it.
not R.
Yeah. So let's put them in alphabetical order. Not P and what else is coming out of here?
Not Q
Yep, not
and
Q. Good.
not R.
That's right. Great. Now we're almost there. Now we've got these three expressions. These outputs from these AND gates are being fed into a big old fat OR gate. That means all these are getting ORed together. So our final answer is what?
P and not Q and R, or
Good.
P and not Q and not R,
Good.
or not P and not Q and not R.
Exactly. And that is in disjunctive normal form because it's a disjunction. The last operator that operates is this OR gate, the OR operator. It's kind of like the big operator. It's the last one that operates. And in these components that are getting ORed together, each give a complete description of the input wires. This says P is hot and Q is cold and R is hot. Or if P is hot and Q is cold and R is cold, we're going to get hot output. Or if P is cold and Q is cold and R is cold, we're going to get hot output. And disjunctive normal form, if you remember from our lecture, it's really nice because it gives us an easy way to get the IO table immediately, directly from the Boolean expression, if the Boolean expression is in disjunctive normal form, because it tells us exactly which rows in the IO table are going to get a 1. We're going to want a 1 in the row where P is hot, 1, and Q is O, and R is 1. Or we're going to want a 1 when P is 1 and Q is O and R is O. Or we're going to want a 1 when all three of the inputs are O. Shall we practice making the IO table?
Yeah, yes.
No. I'm going to see if I can fit it in here. P, Q, R. Okay, so lends itself easily to the IO table. All right, so I'm going to make these kind of small. 1, 1, 1, 1, O, 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 O. So it'll fit on the same page. 1, 1, O, O. I'm going to line this up. 1, 1, O, O, 1, O, 1, O, 1, O, 1, O. Okay. So we're just going to fill in the correct values. I'll just put my horizontal lines like that. There we go. At least we've got some horizontal lines. Put in the output values. We want a hot output if this happens, or if this happens, or if this happens. Right?
So,
So which go ahead.
yeah, it will be 1. I'm sorry,
Well,
not P, not P. Yes, so
P and not Q and R. Which row does that happen in?
mm, the second, I mean third.
Third, yeah. This row right here is P and not Q and R. Yeah, that's definitely the third row. So we want a 1 there. Which row is P and not Q and not R?
The fourth.
So P, yep, because P is hot, Q is cold, and R is cold. So we want a 1 there. And then we want a 1 when P and Q and R are all cold. Which row is that?
The last one.
That's right. Not P and not Q and not R is this last row, so we want a 1 there. And then we just put zeros, O's, everywhere else. Does that make sense?
Can you explain the last row? How did it get like 1 there? Oh, yeah,
Because
where
this
is
expression tells us when the circuit should give hot output. It actually is a description of when this output wire should be hot. In other words, if we put a little light bulb attached to this output wire, it tells us when that light bulb should light up. It should light up on this input or this input or this input. So the 1 in the output column means the output is hot and the bulb will light up. So it should happen if it's P and not Q and R. So in that row where we have P is 1, Q is O, R is 1, that's P and not Q and R. We want a 1 there because we want hot output to light up the circuit if this is happening with the input. Or we want a hot output if this is what's being input, and that happens in row 4 when P is a hot wire and Q is a cold wire and R is a cold water wire. We want hot output, and it will work out. If you feed through a 1 for P and an O for Q and an O for R, this middle AND gate is going to have a hot output from P is 1, because if P is 1, this 1 comes into this AND gate, it's hot. Q is O in row 4, so when O goes through this NOT gate, it flips it to a 1, so we've got not O, which is 1 coming in, and then the other wire that's coming in to this gate is the NOT R wire from this NOT gate. But then if R is O, then NOT R is 1. So all 3 of these wires coming into this AND gate will be 1s when this is the input. And that
Oh,
makes a hot output on this AND wire. And when you put a 1 into an OR gate, doesn't matter what's going on with the other 2 wires, this OR gate is going to output a hot output if any of these input wires are hot. See, this top wire is going to be hot under these circumstances. This middle wire, this middle AND output wire is going to be hot in the row 4 circumstances. And this bottom wire feeding into this OR from this bottom AND gate is going to be a hot wire in the case that all 3, P, Q, and R, were cold, because they all get fed through NOT gates before they go into this AND. And they're all hot coming in if they were cold to begin with. You see what I mean?
yes, I see. Now I get exactly. So there is like P and like there is 0 and Q has 0 and R has 0, and then it will go like P will go through the NOT gate. It's like 1. It will turn to 1.
Yeah. Yeah. If P is O, it goes through this NOT gate right here and it becomes a 1, right? If you feed a 0 into an O into a NOT gate, the output is a 1, right? So that's why this AND gate has a hot output exactly in the row when all of the original P, Q, and R wires were cold, because all those wires get fed through NOT gates before they feed into this AND. That's exactly what's going on. Good. Nura, did that help?
Yes, that did. I just had one question.
Sure.
So When we went through the circuit following the P, Q, and R values and the
Uh-huh.
gates,
Uh-huh.
we were determining the input for the circuit.
We were actually when you mean when we came up with this Boolean expression or when
Yes.
all right, so we were following the wires like this is P until it goes through an AND gate. When it goes through the AND gate, it's P being ANDed with whatever else came into that AND gate. Well, what else was coming into this AND gate? Well, this wire right here was a not Q wire because Q was fed through a not gate before that wire came into the AND gate, you see. So it's sort of a combination of kind of reverse engineering and going forward.
But we wound up with the inputs for our I/O table.
Exactly, because I drew this circuit knowing enough about disjunctive normal form. I planned it before I drew it, that it would come out to be disjunctive normal form. Because in disjunctive normal form, all the NOT gates execute before the AND gates, and all the AND gates execute before the OR gate.
Oh.
And that's always going to be, and I made sure each AND gate had three inputs, one about the P, one about the Q, and one about the R, whether they were hot or not. See what I mean? Now, if this had been a circuit with a P, Q, R, and maybe another variable like a T, then each AND gate would have had to have four input wires so that each of these parentheses expressions would have given information about P and about Q, about R, and about that fourth variable T. See what I mean? So it just,
Oh.
so it just depends upon how many inputs you have. Like we can do disjunctive normal form in a much easier case. For example, one more. Let's see. Find the Boolean expression. If we just have a P and a Q, okay, well, the NOT gates happen first, but maybe, they don't have to even happen. We could run P and Q through an AND, but then we could take the Q and run it with a not P through an AND. You see how each of these AND gates only need two input wires, right? And then we send these outputs from the ANDs into an OR. But this will still be disjunctive normal form because the NOT gates happen before the AND gates, which happen before the OR.
The first output for the first AND gate is P and Q.
It sure is. And
The
this,
second,
yeah,
that's not Q. Oh,
uh,
not P.
not P. Good. So what's the output on this from this AND gate?
Q and not, or not P and Q.
That's right. So since we only have two inputs, these outputs from these two AND gates give a complete description of the inputs. And now finally, the Boolean expression.
P and Q or not P and Q.
Yep. So if we, so you can, make your IO table directly from this expression because it's in disjunctive normal form for two variables, P and Q. Where would the ones go? In the output column. Which row?
The first row for P and Q,
Yep.
and the third row for not P and Q.
Perfect. And we don't want hot output in any other circumstance. So we put O's here and here. Now, it turns out this expression can be simplified. So just as a quickie review, using logical equivalences to simplify Boolean expressions, I'll do this one. P and Q, or not P and Q. Now, there's a distributive law that says or distributes across and you can check. Theorem 2.1.1, it's in section 2.1. And the way it works is if we have the same component, at least one identical component inside these two and statements, and we do, we have a Q here and we have a Q here, then we can factor the Q out. Okay, and it's getting anded with P or not P. This is by the distributive law. You can check. It's almost easier to use the law the other way to distribute the Q with the and across this or. It's Q and P, or P and Q, or Q anded with not P, or not P anded with Q. You see, it's like distributing multiplication across addition, okay? But you can factor out the common factor. And then we can realize that P ORed with not P, well, just think about it. P or not P. Isn't one of these always true?
Yes.
Because they have opposite truth values. So that's a tautology
Oh.
ended with Q. And the name of that rule, let me just double check, because the name of P ORed with not P, I think it's called an identity law. No. Nope. It's called negation law. P ORed with not P. This is the negation law. See, I can't remember the names without checking in the book. Okay, that P ORed with not P becomes a tautology. And then finally, tautology anded with anything is just that, anything. So now that is the identity law. By the identity law, it says if you take a tautology and you and it with any expression, that is logically equivalent to that expression.
Okay.
So it turns out we built this complicated circuit, right? But really, all we needed was just a circuit that lights up if Q is hot. That's what this amounts to. It amounts to a circuit that lights up when Q is hot. It doesn't even care about P. So how would we draw that circuit? I mean, it's so silly, right? Q straight to output. It's a silly circuit. It lights up, Q becomes the output, right? Q is either hot or cold. S is the same. Q is the output. It's really not even a circuit. You just say, oh, okay, this is all nonsense. We don't need any of this. All we need to know is what's going on with Q.
Wow.
Silly things can happen. But definitely check out this Theorem 2.1.1. I'll share my screen one more time just to show you where it is in the book. I gotta pull up the right I gotta pull up the right. Oh, for goodness sake. Where is it? Oh my gosh. Did it log me out? I hate that. I hate when Blackboard logs me out. I'm like, what? Did it really? Oh, forget it. Forget it. You can look it up yourself. I'm not doing it. I'm not doing it. I'm not even doing it. Not even doing I'm not going there. You can look it up yourself. I'm so sorry. That is crazy.
2.1.1.
It's theorem 2.1.1. Yeah, it's in chapter 2.1. If you just search theorem, yeah, theorem 2.1.1, theorem 2.1.1. And there's a prompt to that theorem with a link in the WebAssign. Like, it says use 2.1.1 theorem. It's got all those logical equivalences that we were just looking at. One of the measure 2 practice worksheets gives you an opportunity to play these logical equivalence games as well.
Is that in the special homework?
Yep.
Okay, all right.
I think it's called Circuits and Boolean Expressions worksheet or something like that. And then I just added a new worksheet on drawing circuits for binary addition using adders and half adders. That's what we're going to do tomorrow in class. We're going to learn how to build a circuit that actually correctly adds binary digits. We're going to learn to add. Suddenly trues and falses become real, actual numbers, ones and O's in the binary arithmetic. That's what's going to happen tomorrow.
Are we going to have modus tollens and modus tollus on our quiz? I'm sorry for my pronunciation.
Modus ponens and modus tollens. I think the quiz, I'm going to give you an argument form and just ask you to figure out if it's valid or invalid using the algorithm.
Okay.
Okay. I'll be happy if people can do that. Because when you work your WebAssign homework, you can look up modus ponens and modus tollens and converse error and inverse error, like you can have a reference in front of you, right? I'm not as concerned about you learning the names of those argument forms as you're being able to figure out if a given argument form is valid or invalid, whether you know the name of it or not.
Okay.
Right? I mean, like, that's really the most important thing. You can always look up the name of something, but you can't always look up whether or not an argument form is valid. Sometimes there's not a name for it. You have to actually execute that algorithm. The step 1, build the truth table. Make sure you have a column for each premise and a column for the conclusion, right? Step 2, remember what step 2 is? After you
Yes. Oh,
go ahead. What's step 2
oh,
after we label our premise and our conclusion columns?
we fill in the values.
Yep, we fill in all the values. And once we have our premise columns made and our conclusion column made, then what do we look for?
We identify rows of interest where
Yeah,
all of the premises are true.
exactly. Identify the rows of interest that have all true premises, because those are the rows when we have a true hypothesis of our argument, right? Premise 1 and premise 2 and ... and premise whatever, however many there are, P sub k, are all true in those rows. Then what do we do?
We look at the conclusion value for each of the rows of interest.
That's right. We're checking to make sure the conclusion of the argument is true whenever all the premises are true. We want the conclusion to be true when we had a true hypothesis. And then we make a decision, right? Based on what we saw.
Yes, if all of the conclusions for every row of interest is true or are true, then we have a valid hypothesis,
We have a valid argument.
a valid argument.
A valid
If
argument.
any of the conclusions for the rows of interest are false, even one, then our argument is invalid.
Exactly. Very good. You should do perfectly fine. And how many rows do we need in our truth table if we have a P, a Q, and an R?
We need 8 rows.
We do. We need 8 rows, just like we saw in our IO table tonight. If you have P's, Q's, and R's, 2 choices for P, it's true or false. So true, 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 false, 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 false. 2 choices for Q, it's true or false, times 2 choices for R. 2 times 2 times 2 is 8. That's how we get our 8 rows.
I just mentioned about the IO table. I was actually, and I understand that it's different from a truth table, but I got confused because I thought we were supposed to have not columns,
Uh-huh.
but that's not for the IO table.
That's right. IO tables are significantly more clean because we're just saying, is the output wire going to be hot or cold? And it's true, that output wire is associated maybe with a big old Boolean expression that we kind of say looks like a statement form, don't we? Right?
Yeah.
And I have seen people build IO tables, like when I say build the IO table, and they don't want to run all the values through, because it's really, and I've seen them build all of these columns as if it was a statement
Oh,
form to get S. And you know what? I let it slide because the bottom line is just a different way to attack that.
oh,
We're really doing the same thing. But if it's in disjunctive normal form, you can read it right off if you understand what these rows represent in terms of the input. Like this is pretty easy if your Boolean expression is in disjunctive normal form, right? That's
I
why
understand.
it's
Oh,
called the normal form. It's really useful. It's really useful.
I see what you mean. I don't mean to get off on a tangent, but I don't see how you could write out all of those input expressions and figure out S.
Well, you would make a column for not Q, a column for not R, and a column for not P, here, here, and here. Then you would
Oh,
make a column where you anded together P column and not Q column and R column. That would be a next column. Then you'd make a column for this, and then you'd make a column for this. And then the last column would be all those 3 columns ORed together. It would be huge.
wow.
But it's doable, but not a smart way to do it.
Right.
Right. I mean, you'd spend 50 minutes out of a 75-minute test doing that if you tried to do it that way. You don't want to do it the hard way. We want to learn to do things the smart way. Any other questions before we adjourn? Sunita, thank you so much for coming in and helping get this recording started with your good questions about.
Thank you. Have a
Yep,
good
you're welcome. Good night.
Thank you, Professor. Good night.